Let's talk about comments in C. There's two types of comments in C language. The first one is the multi-line comment. And with the multi-line comment, basically you start your comment with a /**, and then either on the same line or any other line, you can start typing any text. And that text can go all the way until the C compiler finds a */ or */. So this can go on and on as long as you want it, or it can be even a single line. So the idea is that anything between the start of the comment and the end of the comment is considered non-compiled code, meaning that the compiler will skip it. This is just for us humans to read. It's not executable code. It's not a statement as part of the program. The reason we need comments is because we want a way to document our code, and for ease of readability, for ease of understanding, and for future references, and for other people who look at our code. Basically, it's just important to remember that the comment is a way for you and for others to look at the code and quickly understand it, or quickly know if they need to take an action, or if something needs to be, communicated to them, etc. Alright, so this is the multi-line comment. This is part of the C language. And I think the C language also borrowed the single line comment from C++. This is how the C++ single line comment looks like. It starts with a //, no space in between. Anything on this line from this point onwards, the compiler will consider it a comment. These are the two types of comments in C. Alright, let's jump over to Visual Studio. Here I am in Visual Studio now, and I have the Hello World from C project loaded and open in Visual Studio. Let's see the comments in action. So the first thing I want to show you is the multi-line comment. Let's say C multi-line comment is like this. And notice how Visual Studio is nice enough and kind enough to actually finish off the comment for me. I'll do it again to show you. If I just type /**, and immediately finishes it off for me. So let's do a multi-line comment. This is my first comment in C program. Okay, so this is a multi-line comment, and you can go on and on and on. Now let's see an example of a single line comment. Let's put a C++ style single line comment here saying that this is the main entry point. Another thing I want to show you is that you can actually mix it with the code itself. I can do something like this. This main has no arguments yet. It doesn't impact the compiler. The compiler is smart enough to ignore it. And even though I wouldn't recommend doing something like this, but I'm just showing you how it can be done. And also you can do something like this. This is the beginning of main function, and you can say this is the end of main. I'm mixing code with the comments. Just want to let you know that it is completely fine to do it this way, so anything after this is completely ignored. As a matter of fact, we can sometimes see in code something like this. We need this for Printf, for example. Sometimes you will see comments like this where people mention why they included this file, and you can see some people doing something like this. End of hello. Let's see, I think I have commented everything pretty much in this hello program, but just to give you an idea about commenting the code. And now let's verify one thing, which is this is not going to break the compilation, and the second thing is not going to impact the output. So Ctrl+Shift+B to compile. Now I'm compiling, it succeeded. Ctrl+F5 to run, and as you can see here, hello world, nothing has changed in the output, which tells you that this is completely ignored by the compiler. This is just for us humans to read and understand the code. So that's everything about comments in here. Let me just clean this up a little bit because I want to talk about commenting out code and uncommenting code. Okay, now let me show you how to comment out code. So one way to comment out code is by doing something like this manually by ourselves. Now the code is commented out. If we compile and run, you see there's no printf output here because we commented out that line. Let me undo that. I want to show you the power of Visual Studio and how we can use this toolbar where it comments out code for us and uncomments the code. First, let me just copy this multiple times. Let's say this is hello world 1, 2, 3, 4. And let's pretend for some weird reason we don't want 2 and 3. Let's comment them out. You can do it this way. You can highlight these two and then go to the toolbar. Click on comment out. See, now automatically it comments out the two lines for me. Let's see this in action when we run. As you can see now, 1 and 4 are actually printed out, but 2 and 3 are not because they're commented out. So commented out code is just like comments, right? It turns into comments. It's not gonna execute. And now let's say for some reason you decided to uncomment. You just select them again and go here and uncomment. This uncomments them for you. Let's see also if we want to uncomment multiple lines like this. Now it's smart enough to see that these lines are actually more than 2 and they're contiguous, so they decided to use like C style multi-line comment. Okay, so let me uncomment. It won't unless you have to select the whole thing. Now it uncomments it for me. There's another entry point to the same functionality from the edit menu. If you go to edit, advanced, and here you can see comment selection, uncomment selection. But this is probably way too deep. It's too many clicks. I think the toolbar is a faster shortcut to this. Also, there's a keyboard shortcut, Control K, then Control C, and then Control K, Control U. If you don't have this visible on your toolbar, just make sure that you right click here on toolbar and make sure that the text editor is selected. That's the one that shows these things in here. And that was it for the comments. See you in the next lecture. Okay, so let's talk about C symbols. As you can see on the screen, the character set that's allowed by C includes capital and small letter alphabet from A to Z, 0 to 9 digits, some special symbols, and the white space, including the space, the tabs, and the line feeds. I just wanted to mention that C is a free-form language that allows you to write your code in any form you want. You can write the whole C program on a single line, but keep in mind that these are the allowed character sets and characters in C. Right, so let's move on to C keywords. So the C89, C90 introduced most of the C language keywords. As you can see on the screen, there isn't many of them. There's only 32 keywords. We're gonna pretty much cover most of them in this course. The C99 added some like 5 new keywords. C11 adds 7 more keywords. In this course, we will cover all the ones that have the check mark next to them. So that's it for now. See you in the next lecture. In this lecture, we will learn about C data types and focus on the basic types. We will look into the C data types and start learning about the basic types that C offers and learn how to display them using the Printf and the special format specifiers that are provided with Printf. By the end of this lecture, you will become familiar with the basic data types in C, so let's get started. The first one we will look at is the basic types, the intrinsic types that are part of the language. In future lectures, we will learn about enumerations, enums. We will also look at arrays and then look at pointers. After that, we will look at structures or user-defined data types, and also we will touch base on unions. This is just a quick overview of all the data types in C that we will discuss and learn in this course. The basic types in C that we will talk about can be categorized into 3 different types. The characters, which are represented by the char keyword in C, and then the integral values. These are like integer numbers, which are covered by the int and long keywords in C. And then the last one is the floating point values that are captured by the 2 keywords in C, float and double. There's also one type or one keyword in C that's called void. However, void is used primarily to declare functions that return no values or to declare generic pointers. When we talk about basic types, void is not going to be discussed. It's just added here for completion. Okay, let's switch to Visual Studio to just do some practice on the data types. Okay, so I'm here on Visual Studio. I'm going to open up Hello World from C project. It's the first one here on my recent list. By the way, you can click on this pin and have it pinned here so that even if you have multiple projects, this thing will stay here for as long as you want it. Let's open it up. Let's start applying some of the stuff we discussed about the data types. We can have a char like this, or we can say signed char, we can say unsigned char, etc. These are the different possible types for char. Okay, so let's put that in a printf statement. Let's say printf char size equals %d, and we will touch base on this in a future lecture, or maybe in this lecture if the time permits. Basically, this is saying that I want to pass you a decimal here after the printf. So I just want to see how many bytes of memory does the char type take. We can say size of, which is a C keyword. You give it anything here as type or as variable, it will give you the size of it in bytes. So let's say char size of our char type. How many bytes of data does the char type occupy in memory? So let's hit Ctrl F5 on the keyboard to run this. As you can see here, it's saying char size equals 1. That means it takes up 1 byte. Maybe I can add the word byte in here as well, just to make it clear. All right, so how is that different from signed, unsigned? Let's see. Copy, paste. I'm going to say here signed char, unsigned char. And here I'm going to have to say signed char, unsigned char. So that way we can differentiate between the three. Okay, so let's compile this and run it. Alright, so as you can see now here, it says char size equals 1 byte, signed char size equals 1 byte, unsigned char size is equal 1 byte. So really the signed, unsigned is not going to impact the size. Just wanted to make that clear. Alright, so this covers the char type. Let's talk about integer type. The integer type, let me borrow one of these and put it here. Printf integer size equals in bytes, and this is going to be size of integer, and we're going to do the same for signed and unsigned, just to show you how many different types you can define with C. So this is signed and this is unsigned, and again Ctrl F5 on the keyboard to compile and run. And let's look here. Okay, so the integer size is 4 bytes. Whether it's signed or unsigned, it doesn't matter. Really doesn't matter in all cases. So we have 4 bytes for the integer, 1 byte for the character. And let's move on to another type, which is the short integer. Since we're still on integer, let's say short integer size of, and here you can say short integer or just short. Let me compile this. Yes, you can just say short or short integer, because the modifier implicitly it will know that you mean, and because it's the only allowed type with short is integer, so it knows that if you don't specify it, that by default it's implicitly integer. Okay, and then even with the shorts, right, you still can do the same thing where it's short, signed short integer, or unsigned short integer. Make this signed, unsigned. And the purpose of this exercise is to show you the different types, basic types in C. And I think you can even do this. You can even do this. I think you can say short, unsigned integer. or you can say even integer short unsigned. So the order is really not important to the compiler. Let's compile and run. Zoom in. So as you can see, the signed short size is actually 2 bytes. It's the last 4 are actually all 2 bytes. So really, when you add the short modifier to an integer on Windows platform, is gonna be short. Integer is 2 bytes. Let me just erase the stuff and just keep it simple though, so we can focus on a single type. We've seen all of these. So let's talk about here long integer. Let's run this. Zoom in. As you can see, it's really 4 bytes. And whether it's signed or unsigned is the same. Okay, unsigned, long integer, unsigned. Run it. It's still gonna be 4 bytes. Okay, so this is still 4 bytes. The unsigned is gonna hold a larger value compared to the signed of the same type. So that's always gonna be true. Also here, since this is a modifier, really you can say integer long or long integer is just the same. The next one is gonna be long. All right, so this one is actually 8 bytes. That covers all the integer decimal types. Let's talk about float types. So the float is the one that takes floating point numbers with fractions in them. It contains both negative and positive. You can see here red squiggly, it doesn't allow you to do that. And it's 4 bytes in size, as you can see. And then the last one, which is the double, see it's 8 bytes. And the last one is going to be the long double. Here on Windows is the same 8 bytes, as you can see. And let me show you another cool thing, which is, as you can see here from the menu on top, right now it's building debug x86. If I switch that to be 64-bit, because x86 refers to the 32-bit version. Even though my Windows is 64-bit, I can still build a 32-bit app to run on it. However, if I switch my app to 64-bit, so now I just switched to 64-bit, I'm going to show you that the sizes are not going to be different. So let's run, compile and run. It's just giving me some warnings, and as you can see here, the size is the same. It's just requiring some specific, like something like this in here to silence the warnings. This is for 64-bit, but still same thing. So let's try even integer size and long size. The long integer, right? So let's say here, integer types on 64-bit version of Windows. So let's make this integer. Make this long integer, and even if you guys are interested, let's do the character, all the ones that we might be interested in, character. And the last one I want to do is the long was 8 bytes on 32. Just want to verify and confirm that 32 versus 64 is the same. Control F5. Okay, as you can see, the integer size is 4 bytes even on 64-bit. The long integer size is 4 bytes. The char size is 1 byte. Long is 8 bytes. They are still the same, just whether it's 32 or 64. Come here, back again. Switch to 32. Compile and run 32. Okay, so the integer is still 4. Long integer 4. Char is 1, long is 8. So as you can see, size is not impacted by whether you compile for 32 or 64-bit. So this is what we tried in our exercise. We tried the char type, the integer types, the long floats and doubles. And we saw that char, signed char, or unsigned have the same size, but this is how you can declare these types. By the way, char alone, the compiler assumes that it's signed if you don't mention the word signed. So char and signed char are the same. Unsigned, you have to explicitly say unsigned. Similarly for all types that take the signed, unsigned modifier. The integer, as we saw, we can say integer, signed integer, unsigned integer. The short integer, you have to add the short to the word integer, and it doesn't really matter which one is first, which one is second. Similarly for long integer or integer long, they're the same, signed and unsigned, and the biggest one of them is the long, signed or unsigned. And then when we talk about real numbers or floating point numbers, you know, there's float, there's double, and long double. So that's all the basic types that we will be using in the C language. Okay, so in this lecture, we discussed the C data types and we focused a little bit on the basic types, and we saw how to get their sizes using printf with the size of operator, and that was like a quick introduction into basic types. In the next lecture, we will continue our discussion on basic types and see how we can display them with printf function. So see you in the next lecture. In this lecture, we will continue our discussion to learn about C data types, mainly the basic types. We will also learn how to display them using printf, special format specifiers. You will understand the data types a bit more and learn how to display them with printf. So let's get started. The basic data types in C that we will cover in this course are represented in this slide. The first type is the char type or the character type, which can be used to actually represent single characters like this, A, B, C, etc. This slide also shows you how much memory each type can take up when you define variables from that type when you start using that type. For example, the char type takes up to 1 byte of memory. However, there's something called Unicode and multi-byte that could take up to more than that. I'm not going to cover that pretty much in this course, but the basic type, the ASCII type of char, is going to take 1 byte. So that's how I represent it here. The next type is the integer type, which is integral values, whole decimal values, is going to take up to 4 bytes in our case. Keep in mind that this information that I'm sharing with you is specific to Windows and Visual Studio platform. The type sizes may be different if you're using a different OS or if you're using a different version of the OS, etc. So always check what the documentation says, but in this slide we're covering the Windows platforms pretty much from Windows XP or Windows 7 all the way to Windows 10. Whether it's 32-bit or 64-bit, some of these types are not impacted by the 32-bit, 64-bit. They're actually, Microsoft chose to keep them consistent for these basic types. Again, check the compiler documentation, check the operating system documentation to verify. Okay, so back to the types here. The integer type takes up to 4 bytes. The long type and integer both take up to 4 bytes. There's another type called long, takes up to 8 bytes. And then the double, which is not an integer. In this case, the float and double are actually both floating points. The float takes 4 bytes, whereas the double takes 8 bytes. Okay, so now let's talk about the modifiers. If we look at the character, it can either be signed or unsigned. For example, 1 byte is 8 bits. If you say signed character, that means you only use 7 bits because the last bit is used for the sign. That's why you have less of a range of values. The signed character is the default. The ones in red are the default. So if you don't mention whether it's signed or unsigned, because this is optional, the default is that it's going to be signed. If you just say char, that means it's signed. But you have to say unsigned if you really want an unsigned character. Okay, so that's the signed and unsigned char. Let's move on to the next one, the integer. The integer takes actually 2 additional modifiers here, but it still takes signed and unsigned. So you can say unsigned integer, or you can say unsigned integer. If you say signed or you don't mention signed, by default it will be signed. So if you just say integer, I want an integer, it's the same as saying I want a signed integer. Unless you say unsigned, then you have to be explicit about it. Unless you say unsigned integer, the compiler will assume that your integer is a signed integer. and by default it takes up to 4 bytes. Now let's talk about the long and short modifiers. If you say short integer takes up to 2 bytes. We can say signed short integer, or we can say short integer, or we can say unsigned short integer. The last modifier for integer is long, and actually long, as I checked with Visual Studio, it doesn't make a difference if you say a long integer or just integer. It's the same size. They're both going to be, in both cases, going to be 4 bytes. So long int or just int is the same. Okay, so let's move on to the next one, which is long. Long is really long. It's like 8 bytes of data. So again, you can say signed long or unsigned long, which is the maximum value. Let's talk about the floating point types, float and double. Float is 4 bytes. It's used for fractions, right? Numbers with a floating point. They're also negative and positive. The other type that is also floating point is the double, but it's higher in precision and can take up much bigger values. So it takes up to 8 bytes. You can also say long double is supposed to be the same size as double or even more. That depends on the compiler platform implementation. This one here is just worth mentioning that the C assumption is that a char is always less than or could be up to a short. A short is less than or could be up to an integer. And an integer is always less than or could be up to a long, which is always less than long. So this is how the C specification mentions it. The different compilers, different platforms may implement this differently based on the platform, but at least they all guarantee that this is the relationship. Similarly, for floating points, doubles will always be greater than float, or maybe in some cases they're as equal. This is 4 bytes, this is 4 bytes. And the long double could be the same as double. For example, on Windows now, long double and double have the same 8 bytes. So this, as long as they're equal to or less, then this is the relation that's mentioned by the C specification. In the next lecture, we will continue our discussion on basic types and see how we can display them with printf function. So see you in the next lecture. Alright, so a special attention is needed for characters versus strings. A character is a single letter, like A or B or C, etc. It takes up 1 byte in size for ASCII characters. Unicode takes up to 2 bytes, multi-byte takes more than that. The ASCII values range from 0 to 255. They're always enclosed between single quotes, like this. When you use a character in C, you have to put it inside single quotes. They can also be treated like integers. So for example, the ASCII value for small letter A in the ASCII table is 97. The ASCII value for capital A is 65. You can easily say capital A, small letter A minus capital A. The compiler will give you 32 because it treats them by their ASCII values, 97 minus 65, etc. So that's characters. Moving on to strings. In C, there is no intrinsic type called string. A string is just a series or a sequence of 1 or more characters. They're enclosed in like this, between quotation marks, not single quotes, but the double quotes. That's how the C compiler knows that this is supposed to be a string versus a character. Okay, so hello is an example, hi is an example. This is a string, even if it includes numbers, as long as it's between quotation marks, it's treated as a string. C strings are null terminated, and we will touch base on that when we talk about pointers and arrays and strings in that lecture. But right now, just quickly to let you know that C strings are null terminated. Null is the 0 value, so each string here in memory will have trailing 0 in here and here. They all end with a 0, not necessarily shown to us, but when they take up memory space, there's an additional byte or 2 bytes in case of Unicode for the 0. So just wanted to let you know the differences between strings and characters. Let's talk about how we use types with printf. We have seen printf in our previous example. We've just passed in a string, but also printf actually can take additional parameters, and these are optional. Inside the format string, we can use a special character, percentage like this, followed by some values that are actually used for replacing the parameters after the string in here inside the string. This is more clear with an example. If I say in my code printf, and this is the first parameter here, the format string, I bought my car in, and I don't want to mention inside the string what year, right? I could pass it in as a parameter in here, or maybe this parameter comes from a file, comes from user input, from the keyboard, etc. This allows you to do like substitution. So when printf is scanning the string, it looks at this and say %d. Well, okay, so that means you want to pass me a decimal value afterwards. So it expects you to have a parameter here that is actually a decimal value to be placed inside. So that's what I mean by this arrow here, that the printf expects at least one decimal in this case to be passed in. Once we execute this code, the output result is going to be I bought my car in 2011, because printf will do the substitution for us. What else can we do in place of this example? Let's talk about the most important type characters that we can use. As you can see here in this table, C stands for character. So I can say printf %C and follow it with a parameter that's between single quotes, because this is a character. It will actually use that and print on the screen the A letter. Again, this is only useful if this data is coming from external sources, not hard-coded, because otherwise I could just put it in here. But this is useful when you start using some external sources like keyboard, files, other mechanisms where we can get the value. Alright, so the next one is decimal, D for decimal. This is a signed decimal integer. So for example, here's an example I have. Printf, I am %D years old, and I have %D phones. The nice thing about printf is that it goes from left to right. It sees this one, so it expects the first parameter here to be an integer. It takes this, puts it in here. It then continues, finds another %D, so it looks for another integer in here. If you don't pass in the required parameters, chances are your code is going to crash, cause you errors. So make sure that you always match the parameters with the number of format specifiers in here. So the output of this is going to be I am 25 years old and I have 3 phones, for example. Alright, so there's also one for floating point numbers, and it's used for both float and double, which is called F for float. So you can say %F and then pass in a floating point number here. The second one, which is also important, is the string. S stands for string. You can call me %S, for example. It expects this parameter, the first parameter after the string, the format string, to be another string. John Doe is going to be replaced inside. I'm hard coding the values here just to show you examples that you can quickly understand. There's also one that's worth mentioning here, which is the X. This actually turns your integer number into hexadecimal. So if you say %X, it will turn this 16 into hexadecimal. So that's just an example of using the hexadecimal values. And finally, I'm added the unsigned decimal here in case you want to use unsigned values, and this will show you. On this example, I'm showing you that this is one advantage of using printf like this. If you have a calculation, for example, it does it for you, show you the output. Okay, let's switch to Visual Studio. Just do some practice on the data types. Okay, so I'm here in Visual Studio. I'm still using the Hello World app, and I have cleaned it up again to go back to normal state. So let's see how we can use printf with the format specifiers we learned. I'm gonna say printf, my name is %S for a string. Then I'm gonna say here, and I am %D years old. So if I pass it Mo, then I want to quickly calculate my age, 2016 for example, minus 1973, and let's compile and run. Okay, so now as you can see, it says hello world, my name is Mo and I am 43 years old. All right. Okay, what else can we do? Let's try Printf. Did you know that %c minus %c equals %c, and if we say a minus comma capital, so these are separate parameters, a, and then a minus a. Okay, and let's run this. Okay, so it says, did you know that a minus a is 32? And I forgot a new line character in here. Put \n for new line. And let's try the hexadecimal one. 16 in hex equals %x, as we said, for hexadecimal, and we put 16. And let's Control F5, zoom in. 16 in hex equals 10. All right. So, and by the way, let me try something else. Let me try 15, because 15 is more interesting. In hex, 15 is letter F. As you can see, it's small letter F. However, because I'm using a small letter X here, if I say capital X, then it will actually show me a capital letter instead, as you can see here, which is also cool. And I think that's pretty much it for Printf with the types and format specifiers. Please give it a try, do it yourself, and we'll start practicing more and more with the future lectures. So as a summary, to recap, we discussed the C data types, we discussed the basic types, and the format specifiers, and that's it for this lecture. In the next lecture, we will talk about variables and how to use variables, how to declare them, what are they. So see you in the next lecture. In this lecture, we will talk about variables and learn how to declare them and use them. We will also talk about constants. By the end of this lecture, you will understand how variables and data types work together, and we will start building some more meaningful programs. So let's get started. First of all, what are variables? A memory location to store data. We give it a name so we can refer to it and access its data. The reason it's called a variable because we can change the data it contains, also referred to as its value. It also has a type, so it can be of type character, integer, long, float, double, etc. Why do we need variables? Well, because most of our programs need to manipulate and process data, and that's why variables come into play and help us with building meaningful programs. So how do we declare a variable? This is one way to declare a variable. However, we do not know what kind of value will be contained in that variable because, as you remember, it's a memory location, and if we don't put any value there, by default the C compiler will just leave it as is. Whatever value is in that memory location that we get is going to be the value inside it. So consider that value as garbage. Another way to do it is by saying integer age, and you give it a value. In this case, we assign it the value 32. So we declare a variable of name, age of type integer, and we store inside it 32. The first thing we do is specify the type. Then we specify the name of the variable, and then we initialize it to a value by assigning the value to it. Imagine in your memory, you have a lot of memory. Somewhere in memory, when you say integer age, you will get a memory location, right, to store your data. The compiler does this assignment for us. Behind the scenes, it knows like, okay, I need to track a variable of type integer in a memory location, and in that variable, I'm going to assign the value 32. So the memory actually contains the value. Your variable name is just kind of another alias for that memory location. So exactly the whole time this variable is alive, it's going to be attached to a memory location, and its value is contained within that memory location. So every time we change the value, it's being changed here. Alright, so let's jump into Visual Studio and start doing some practice with variables and also talk about constants. Okay, I'm here in Visual Studio. Let's quickly create a new project. Hit File, New Project. Okay, from the New Project window, make sure you have Visual C++ selected. Take Win32 console application. Let's call this one Variables. Hit OK. On the next page here, we're going to hit Next. And then make sure to select Empty Project because we don't want to create a CPP project or C++ project. We want to create a C project. So hit Finish. Okay, so now on the Source Files folder, right-click and click on Add New Item. And let's name it My Variables. Let's see. Okay, let's say include standard io.h. And we say void main. Alright, so now we have our program ready. So let's start declaring some variables. The first thing I'm gonna do is say integer age equals 32. Then here we can say printf my age is %d because this is a decimal. And we can type the age here. So this is, we just declared an integer variable, assign it to 32, and then we're now displaying its value. Let's do something more interesting. Integer sum equals 1 plus 2 plus 3 plus 4. Sum of 1 plus 2 plus 3 plus 4 equals sum, just to show you like how we can calculate the sum. We can also calculate the average. Integer average equals sum divided by 4. Then we can say average equals avg. We'll talk about variable naming conventions and stuff like that in future lectures, but for now just practice on getting familiar with the variables, etc. Let's compile this and run it and see how it goes. Ctrl F5 and then zoom in. So my age is 32. It did a substitution. Sum of 1 plus 2 plus 3 plus 4 equals 10. Average is 2. You may be wondering why the average is 2. Just to give you an idea, the division here is actually an integer division. So there will be no fractions because the two numbers we have here are actually integers. And even the variable that holds the value is going to be integer. So this is not going to show us any fractions. So let's try with float. Let's say float. And this is where it gets interesting. If you say average 2 equals sum divided by 4. And this, let's call this one integer average, and this one we call it float average. And this is average 2. By the way, I think this is just to give you an idea how you can name your variables. The variable name should at minimum start with a letter, right? It cannot start with a number or a special character. You can, for example, say 1 at the beginning here. It will give you an error. See the squiggly here is not happy about it. So it should always start at a minimum with one letter. Even if you do it like this, that should be fine. Always try to give your variables meaningful names. And there are some guidelines on how to name variables. We'll touch base on that in future lectures. Right now, I'm just trying to get you to practice with variables, etc. So Ctrl F5 again. Okay, so I'm getting some interesting things here. And this is why it's useful to play with the compiler and see what's going on. It says initializing conversion from integer to float, possible loss of data on line 9. Let's go to line 9. Control G 9. This is Control G, by the way, gives me an option to go to the line. I could have also double clicked on this guy here. And as a matter of fact, I don't have the line numbers on. I should turn them back on. Options, languages, line numbers. Okay. I just turned the line numbers on. So the problem here is that this number is integer and it's dividing by another integer, so the result is going to be integer. And this warning is telling us that we're going to lose some data here. So the fix is to make one of them as a float number. So we have to say 0.0, but we also have to say an F at the end, which means it's a float number, make the 4 as a float number. This is one way to fix it. So you see now that first warning is gone. Or we could just simply use a typecasting operator in here and force it to be float. We do it this way also. That's another way to do it. Let's not talk about cast operators yet, but let's just do it this way. Alright, so the second warning we have is that I forgot to here say %f. This is actually a very nice feature of the most recent Visual Studio. Older versions may not give you this kind of warning. So this one is very nice. It's telling me, hey, did you mean something else here? Because this is not matching with the specifier here. So now let's compile. Okay, Control F5 to run. Let's take a look now. As you can see now, the integer average is 2 while the float average is 2.5. So that's the difference between integer division and float division. Also, like I said, for example, we can come here and say age is now equals 40. And if I do another printf here, let's try it again, then that should show you a new value. Let's run this. Okay. You can see now my age is 40. At the beginning was 32. So we have changed the value that age is actually holding. Another way to change it is you can say age equals age plus 1. You can do something like this. And there's also some neat C increment operators where you can say age plus plus incremented by 1. This is just a shortcut. And also they say plus plus age. Or you can say age plus equals, for example, 10. I think we should cover all kinds of operators in a future lecture. Okay, let's talk about constants now. A constant is simply like a variable, but you can precede it with the word const. When you use the keyword const in C, that means that this is an integer constant, not an integer variable. See the minute I did const here, this line here, once you say it's constant, that means its value cannot change. So you cannot actually change its value. This will not compile. This is an error because you're trying to change a constant. I could have changed anything else but the age here because it's the only constant we have. Any variable type can be constant, and constants are usually useful in cases like where you want to enforce a specific value. For example, you can say const float pi equals 3.14. Alright, so let's compile this using Ctrl-Shift-B on the keyboard. And as you can see here, I'm getting a warning. The nice thing about, let me zoom in. As you can see here, I'm getting a warning, initializing truncation from double to const float. I'll tell you why, but before I tell you why, just to show you a cool feature here, I can actually put the cursor here on the warning, hit F1 on my keyboard. That will launch the MSDN, the Microsoft Developer Network documentation, and it will tell you some more details on this warning. Compiler warning C4305, the one we're getting, says truncation from type 1 to type 2, and it gives you some explanation. In this case, unfortunately, this is not very helpful, but some other cases I find the explanation very useful with some examples, etc. So back here to our problem. In fact, what's happening here is that by default, all floating point numbers are actually doubles in the Visual C compiler. See here, if I hover on it, it says double. As you can see in this little tooltip, it's saying double. It's really a double, and it thinks that you're trying to fit a double inside a float. To get rid of this annoying warning, we just put the letter F here. This means that this is a float number. The other one that you can use is, which is L. This stands for long double. You put it as an L, then as you can see now, it's long double. You put this as an F, then now it's actually a float number. Okay, so that gets rid of that warning. All right, so you might be asking, why do we need constants, right? One good example is like we saw in this previous example where you guarantee that this value is not going to change. For example, if I say const integer my app version equals 1, or yeah, let's say 1, right? This is version 1 of my app. Then everywhere you reference and use this my app version, you know that nobody's going to change it throughout the code, or you're not going to change it yourself throughout the code. You just define it once and use it everywhere. That's why it's useful, right? You can, because if you use one everywhere, you'll be confusing yourself. Like, what does one mean? Why did I use one here? Another thing I wanted to mention here is that most people often tend to use all caps for constants so that they can easily differentiate them from other variables. So that's it for variables and constants. See you in the next lecture. So in today's lecture, we're going to learn about a new data type in C++ called the enum or enum data type. Okay, so here I am in Visual Studio. Let's go ahead and create a new project. Click on File, New Project. Make sure to select Visual C++ and Win32 console application. Let's call this one enum data type. Click OK. On this page, click Next. On this page, make sure to select Empty Project, then hit Finish. Alright, let's go ahead and add our source file. Right click on Source Files, Add New Item, and let's call it main.c. Click Add. Okay, in today's lecture, we're going to learn how to declare and use enum data types in C++. Enum stands for enumerated data types. This is used to define name constants. In other words, we can give names to our integer constants. So how do we define enums? Basically, the way to define it is you use the enum keyword followed by the name of that enum, and then a list of all the values that belong to that enum. And optionally, you can add a variable name in here, and then you have to end it with a semicolon. We have seen before that we can define const integer, like for example Sunday equals 0, const integer Monday equals 1, etc. There's an easier way to do that using enums. Instead of doing it this way, we can just use an enum data type, enum days. We have to use the curly braces here and end it with a semicolon. Now we can introduce our values that belong to this enum. We start with Sunday. Then we can say Monday, Tuesday, Wednesday, Thursday, Friday, and then lastly Saturday. So now what I did here is basically I defined a new data type called days that has the values starting with Sunday, ending with Saturday. By default, the C++ compiler will give this a value of 0, and then it keeps adding 1 to the previous one, give it to the next one. So that means it's become 0. This is 1, 2, 3, 4, 5, 6. You can actually change that. You can say this is equals to 1 instead of 0, and that becomes the new value for Sunday. And then typically, if you don't specify 1 here, then it takes the one before, adds 1 to it, and makes this automatically becomes 2. So let's just leave it as is here. We can define a variable here inside main called enum days my day. This is one way to do it. Another way to do it, when you define the enum itself, you can say here my day variable. Most often people just actually define it when they need it. So I'm gonna get rid of this. Right, so now we have defined my day. I'm gonna say my day equals Sunday. I'm gonna printf. It's an integer constant, so we're gonna see that now by printing out the value here. Then I'm gonna change the value my day again equals Tuesday. Then say copy this. Right, so let's compile and run. Ctrl F5, like yes. So as you can see, Sunday equals 0, Tuesday equals 2. That's because Sunday started with 0, Monday is 1. Actually, if you hover on it now, you can see the values here. It tells you what value they have, which is cool. So the other thing I want to show you, like I said, you can actually change the value. It's possible to give it the value you want here. Like right now, Sunday became 1, and then as a result, Monday became 2, Tuesday 3. At any point, you can come and change. I want Tuesday to be 20, for example. I can totally do that. See now, Tuesday is 20, Wednesday is 21. So if I run this now, it's going to give me 1 for Sunday and 20 for Tuesday. Let's see that in action. Ctrl F5. Yes. As you can see, Sunday is 1, Tuesday is 20. Okay, this is pretty much how you define an enum and how you can use it. Just a few things to notice here that, first of all, the word enum, I typically pronounce it enum. I've heard other developers say enum. So enum or enum, it doesn't matter. Just pick whatever you feel more comfortable with. The other thing I want to mention is that some developers like to make it capital case because it's a constant. I've seen also people where they prefix it with an E, for example. I've done this myself several times so that I remember this is an enum. Pick whatever you feel most comfortable with and use it. So these are the things I wanted to mention. Please make sure that you write your own sample write your own code. Another example that I could mention here, for example, is, let's say, months, right? We can even define the months of the year. January, in this case, I want January to start with 1. And in fact, let's just put this back to normal, because 0 through 6 is good enough for days. Whereas in months, we can start with 1 and then go on and on. This can continue for all the months of the year. So this is how you define enums, and then this is how you can use them like this. All right, see you in the next lecture. In this lecture, we will understand the C variable scope. We will learn how to declare and use both local and global variables. By the end of this lecture, you will understand the variable scope rules in C and become more familiar with how to declare variables both global and local. So let's get started. Okay, so here I am on Visual Studio. Let's go ahead and open up the project from our previous lecture on variables. It's the first one here. I'm going to click on it. All right, so today we want to learn about variable scope. The first thing I want to do is clean up some of this code because I don't need it. And let's just keep the age. So in this case, we only have one variable here defined, and we print out that variable. As you might guess, this variable right now is considered a local variable. This is local variable. In C, there are two types of variable scopes. Either a variable can be local or global. So if the variable lives inside a function, like this case, age lives inside the main function, in this case, age is considered to be a local variable. What do we mean by a local variable? Local variable means that its scope, lifetime, and visibility bound to the code block it resides in. But really, this guy is only visible in this code block, and it only will live as long as this code block is being executed. So meaning that whenever you start executing, you get to this line here. This is when we declare, define, initialize the variable. And then once we come to this line here and we exit, so when we're out of this scope, the C compiler will actually get rid of this variable, will get rid of this memory and not use it for our variable anymore. So the variable really lives between these two curly braces. Okay, so what happens if we actually define a variable outside the function, like let's say integer a here? Well, in this case, this variable is actually a global variable. Global variable meaning that if we have multiple functions in the file, they will all be able to see and access a. This is also considered as program-wide variable. If your program is divided into multiple files, you can still access this from multiple files. We're not going to see how to do that in this lecture, but just to give you an idea. So let's just focus on two things, global versus local. All right, so what happens when we don't initialize a global variable? Well, in some C compiler implementations, globals are usually initialized to 0. However, don't rely on that. You should always initialize your variables. The next thing we want to talk about is what happens if I have an integer age here as well. Let's call it, this one is 40. Right, what's going to happen in this case? If we come into our main function, we have a global age and we have a local age. First of all, is this something that's going to compile or not? Well, let's see. Ctrl+Shift+B. Yes, it compiles. So it's allowed actually to have the same name, whether it's local and global. They can have the same name. But now the next question is, which one of these two actually is going to be printed out here? Well, if you guess that this is the one that's going to be printed out, then your guess is right, because the local scope will actually hide the global scope. So let's Control F5 to run and see this one. So you can see now 32 is displayed. So as you can see, there's a global scope and a local scope. You can do something like this, because this is another block, you're allowed to do something like this. What if I come here and say integer age equals 50? Well, that's also valid in C, right? Because this is considered now a new block. Now, let's say I want to print out one time here and then one time here. Now let's ask ourselves the question, in this scope, which variable is going to be actually printed out? If you guessed 50, then you're right. Let's even make it more complicated and say age now equals 60, right? Let's see, do it this way. Now, what is your guess for this one here? What's the output here? Is it going to be 60, or is it going to be 32, or is it going to be 40? So if you guess 32, then you're right, because as you can see, this integer local age is bound by this block. So its lifetime is between this point and this point. When we get out of here, then this one is going to take over. If we did not have this one, then the global will take over. But anyways, let's see. The output we expect here is going to be 32, 50, and then we should have 32 according to the rules of C variable scopes. So Control F5 and see how that goes. All right, so you can see we have 32, 50, and 32. So like I said, even though we have a global here, when we go inside main, the local takes over, prints out 32. When we get into this block scope, this one takes over, prints out 50. This 60 is actually changing this local variable, not this variable, not the global one. When we come out of this one here, we just change 50 to 60, and then this variable is now no longer available. We come back here, this is the local age here, 32 is going to be printed out. Okay, so now let's see if we just get rid of all this. Let's keep one printf. And now let's actually comment this line out. Now we should be able from main to access the global age. So now if I have Control F5 on the keyboard and run it, as you can see now, it's actually accessing the global age. So this is pretty much all we need to know right now about local versus global scope. More about block scope in C. Okay, so just to understand the block scope and how it works in C, if you are using a compiler other than the recent Visual Studio, you might run into issues with the local scope of a variable in C. Even older versions of Visual Studio, for example, here I have the very old version, Visual C++ 6. It goes back to 98. So this is one of the older ones. I'm going to show you here where you might run into some issues and how to just pay attention to that. So let's create a new project. I'm going to create a new 132 console application with this old thing. I'm going to call it test block scope. Okay, it's going to be an empty project in my case. I'm going to click finish. Okay, so I'm going to add to this my first C file. I'm going to say add new file from here, file new. I'm going to say C++ source, but I'm going to give it main.c. Click OK. Right, here's my main.c. I'm just going to say include standard io.h. There's a slight difference between block scope in C and C++. Especially with older compilers, older versions of the compilers like this one. If you define a variable, for example, let's say you have some code here for integer I equals 0, I less than 10, plus I. Say we want to print out I equals this variable. Okay, so in this example, we have a for loop, just a simple for loop. If we try to compile this, compile main.c, as you can see here at the bottom, we're getting a syntax error. This is because in this version of the compiler, this here is not allowed. You cannot make the I here as a part of the for loop. So in fact, this is going to be one of the problems you might run into. So you cannot do this. So instead, you have to take this thing out and make it into a variable here. You can only define local variables just right after the curly brace. So now if we compile this again, compile, now as you can see, 0 errors, it's working fine. Okay, so this is one example. Another example is, let's say I'm writing some code and I want to define integer a equals 100 here. And I say printf a equals its value here. Let's compile this again and see how it goes. Again, we're getting another syntax error, missing semicolon before type. So this is again another problem we have in older compilers of C. So how do we solve this? Two ways to solve it. You can move this up here to the beginning, and that's why you will see old C code that has all the definitions at the beginning of a function or a beginning of a block scope. So this is one way to solve it. Let's compile this, build, compile. Now it has no errors. Another way to solve this is that you can just simply come here and do this, which is not really recommended, but this is just to show you that the compiler allows you to define variables at the beginning of a curly brace, which is called, this is called block scope. That's why it will be allowed. So if we compile this, again, this is compiling fine. So typically we don't do this, but we could do this if we have like an if statement, if I is greater than 10, or for example, if I is greater than 5, then can we do this? This is one way to do it. Another way is to just move this up. The main reason I wanted to mention this is because you may not be using the latest and greatest Visual Studio. You might be using an older version of Microsoft compiler or an older version of some other compiler. You might run into this issue. I just wanted to make sure you understand the problem and how to fix it. So that's it for this lecture. In this lecture, we will understand how to write and call C functions. You will start writing your own functions by the end of this lecture. So let's get started. Let's take this example where we're trying to create a function that adds two integer numbers. So the function name is add, and it takes in an integer a and an integer b. And basically what it's doing is just adding both numbers together and returning that result to the caller. So let's try to dissect this function. As you can see, the first thing is this line above here is considered to be the function header, or also referred to as the function signature. The prototype has a slightly different meaning. We will cover that in a future lecture. The first thing you see here, this is the value that the function returns, is known as the function type. So in this case, the function is returning an integer. The function name is usually the one that follows the type. There are two different coding conventions that we should probably cover in a future lecture. But for now, let's say that we want to stick with the one that capitalizes the first letter of every word. The argument list to function is the one that is between the two parentheses. If your function doesn't require arguments, then you don't need to pass in any arguments. In that case, this will be empty. This function in this case requires exactly two parameters. So you cannot call this function unless you pass it two integer values. This curly brace here is actually the start of the function body. And then the bulk of the code, all the statements inside the function, are what we refer to as the function body. And then finally, the function ends with its last curly brace. So these, remember that they always have to match. So that's how we dissect a function. If the function that you want to write does not return a value, then you use the void keyword here, meaning that it doesn't return anything. In that case, there's a slightly different name for it. You might come across the name procedure instead of function, because a function is expected to return a value, whereas a procedure does not return a value. In that case, it just executes a set of statements and returns nothing. A procedure usually means it doesn't return any value. Alright, so enough of talking. Let's jump into Visual Studio and start writing some functions and see how we can put functions together to call each other, etc. Okay, let's go ahead and create a new project. Click on File menu, New Project, and then make sure you have Visual C++ selected, Win32 console app. Let's call this one Functions. Okay, click Next. Make sure you click on Empty Project and hit Finish. Now we want to add a new source file, so right click on Sources, Add New Item. Make sure you select C++ file and then change the name to myfunctions.c. Just make sure that the extension is .c. Just put a comment, functions in C. Alright. As usual, let's just do the include standard IO.h, then void main. Okay, so now we have our first function written, right? Because main is a function. So what we want to do next, normally we say like printf hello world here, right? So normally we do this printf, and as you can see, our main function is calling another function called printf, which is defined inside standard.io.h. Let's see how we can actually put this in another function here. Let's call this function void say hello. I just did a Control X on the keyboard so I can cut the text, and now Control V to paste it again here. So now say hello is actually a procedure, it's not a function. Procedure, because it returns nothing, right? So this is our say hello procedure. We can come to our main function called say hello from within main. So this is actually main is invoking the say hello function or procedure. Okay, so that's the first thing we want to do. If you want to test this out, let's hit Control F5 on the keyboard. Yes, to compile and run. Okay, as you can see, it's the same output, right? It's just now we put our code in a separate function. If you start writing a lot of code, it's a good idea to actually break it into functions and make it more modular this way. But we will cover that in future lectures, especially when we talk about how do we split into multiple files, how do we create our own header files, etc. Okay, let's say we want to build a function to add two numbers together. So, and by the way, you cannot implement a function inside a function. It's not allowed. In C, you cannot nest functions inside each other. If I try to put this inside main, that will cause compilation errors. Your functions are always more like siblings, right? They can't be children of each other. Okay, let's create an integer sum function which takes in two integers a and b and returns an integer. So this function takes in two numbers and returns an integer. One way to implement this is to say integer result equals a plus b, return result. Right, this is one way to do it. And by the way, we're using the word return here. I haven't mentioned the word return before, but this is a C keyword, meaning that this will be the returning value from this function. And it has to be exactly the same type as the return value. So return returns from this function. It stops, even if you have some more code here, if you say result equals 100, for example, this is not going to get executed. Return statement will immediately end this function and go out. So this code is unreachable. By the way, you can also do it in a different way. You can say return a plus b. That's also valid. We don't need that result temp variable. This is as good as doing the previous version, which is the one we had before, like this one. Both are equally the same. The only difference here is that this defines a temp variable. So if you're trying to debug and see the result before you return from the function, then this might add a little bit more extra information for you. Okay, so now that we have our function defined, and by the way, this is called the function definition. And now let's see how we can call it, how we can invoke it. So let's say integer n1 equals 10, integer n2 equals 20, and then we can say integer result equals sum of n1 and 2. Now that we're also doing this, let's talk about variables. This variable here is completely not the same as this variable, because this is local variable in this scope, right? It's just within this scope. Once we get out of this function, it's going to be gone. And this variable here, even though it has the same name, it's local to this scope, the main function. In fact, they're definitely going to be living in two different memory locations, because we discussed variables in a previous lecture, so it's good to reiterate over this. Right, so now let's print out the result, printf sum of %d equals %decimal new line character. I'm going to pass in n1, n2, and result. So this will show us the output of that. Let's compile, Control F5 to compile and run. Alright, so let's look here. Hello world, sum of 10 and 20 equals 30, which is correct. This is how we define a function and then call the function. Cool. Let's now try a different function. Let's try average. I can come here and define another function called average, and it takes two numbers, integer a and integer b. We have to specify what value to return, float. And by the way, if you don't specify it like this, it's not the same as void. It assumes this is integer by default. But I'd recommend that you always be explicit and specify what you want. In this case, we want float, because integer division is going to be completely different from float division. Return a plus b divided by 2. And right now, this here is actually an integer. To make sure that it's not an integer, it's a float, we say 2.0f. Okay. So now that's the average. Let's try to invoke it here. And this time I'm going to use %f because it's a float, not an integer. The result is a float. We'll still use n1, n2, and then I could easily say here directly average of n1, n2. So let's Ctrl F5 to see this. So you can see the average of 10 and 20 is 15. One more thing I need to cover here, which is, see this a plus b, just to show you how functions can rely on each other. You can here say sum of a and b, because average actually knows about sum because it's defined right before it. However, sum does not know about average because average is defined later on. So this is another thing to learn about C, is that as you scan the code from the beginning to end, visibility is like this, right? Sum can see hello, and average can see sum, etc. Main can see all of them. In fact, if we put average after the main here and we compile, you will see that we're getting some errors here. Average is undefined, assuming extern, returning integer. This is not right because it's actually inside the same file. It just should be here so that the main can see it. Okay. So now we can see that average is calling sum, even though this is a very simple, trivial thing. It's just to show you how a function can call another function within the same file. When we talk about header files and splitting into multiple files, we'll see a way where regardless of who comes first, who comes last, they can all rely on each other and call each other just by using some other more advanced techniques in C. See you in the next lecture.